Hmm. All right, good morning, everyone. Welcome back to class. Your exams should all be posted and available in Canvas. So if you go into the grade book, you should be able to see the grade. And then if you search around enough, you should be able to find the graded PDF that I uploaded for you. So if you don't see it, let me know. Then when you're looking at your graded exam, just make sure the points add up correctly. Make sure, see if there's anything that you don't understand about the grade. If you have any questions, let me know. I have the exam one solutions here. So I made some minor comments on your exams, but if you want to see the full solution, it's available right here in this document. Okay. Um, so let's see. We are actually getting pretty close to the second exam. Okay, so that'll open in 2 weeks. Right. Today is September 17th. So we're kind of right in the middle of chapter 3, and we're just kind of plugging away, right on track with the schedule here. In 2 weeks, exam 2 will open, so that Monday, the 30th, and it'll be open for 3 days, just like this last one. And it will only cover one chapter. It'll just be over chapter 3. Okay, so do you guys have any questions about that, about the homework, about anything really? Do you want to talk about anything? Are you guys feeling ready to get going here? So what have we been doing? We have been talking about this distribution, this probability distribution called the normal distribution. Okay, so why? Well, it's interesting. We can use it to determine somebody's position in a population, right? So if you have somebody's height, you can determine what percentile they're at. And so that by itself is useful. At the beginning of chapter 3, we the reason we started talking about the normal distribution was because we noticed that in the applet, when we were calculating our p-values, the null distribution, the collection of dots basically, resembled a normal distribution, a bell-shaped curve. And so we're going to come back to that idea now and see how we can use the normal distribution to start doing inference. Okay, so we actually use the normal distribution to do hypothesis testing. So the z-score, of course, is the standard normal score. So it's a value from this standard normal distribution. And we can use a z-score to actually do a full hypothesis test. And we like that. We like our applet, we like our randomization applet, but we also like having the normal distribution to do hypothesis testing. So let's think about how that would work. Let's jump right into this example here. So if you remember back in chapter 2, we looked at this quirky study that was done about head turning. And the guy was trying to figure out if there is a behavioral asymmetry, a preference for turning the head to the right over the left. And so the null hypothesis is that there's no difference, that the percent of right turns should be the same as the percent of left turns, should be 50-50. The alternative researchers' hypothesis is that it's more than 50%, that there are more right turns than left turns going on in the world. And so those are the competing hypotheses. And then, of course, we need a hypothesis, we need a data set, right? So he went out and it's kind of weird, but he basically observed people, right? 124 couples, right? So if we remember the data set, this is nothing new here. We've talked about this example several times. We go 80 divided by 124, and we get our sample proportion, 0.645. So about 65% of people were turning to the right. Okay, we call that p hat. It's the number of right turns divided by the total sample size. Remember doing this? So in chapter 2, we learned how to see if this was statistically significant. 65% is not 50%. It is indeed more than 50%, but is it so much more that we're convinced by it? In chapter 2, we were convinced. How did we get convinced? Because we used the randomization applet. Okay, so Let's go back to that randomization applet and just kind of go through this quickly. We've done this many times now, so should be comfortable with this. So the idea is, okay, if it's 50-50, if there's no preference for right over left, then basically we just got the 65% by chance. And so what we do is we put in the null value here, 50%. We put in the sample size here, and then every time I hit the draw samples, it does 124 it draws 124 trials, and it looks at the number of right turns, right, or the number of heads, basically, right? And so what this allows us to do is to see how much we would expect p hat to bounce around just by chance. Okay, so if the null is true, if there's no preference for right over left, this gives us an idea of how likely it is that we would have gotten 65%, right? You guys remember doing this? So we put in our boundary of 80 because that's how many he got, right? And we start to look to see how many were past that boundary, right? And so I've already hit the button 100 times, oh, almost 100 times now, and we haven't seen a single one that's as extreme as what he got. We got kind of close here. There was one just by chance, and what we see is that it's not very likely that that would happen by chance, right? Because it hasn't happened once in 100 times yet, right? So where do we go from there? Well, we can get more dots, right? So maybe we'll do this 1,000 times. So when I hit the button here, we get 1,000 dots, right? And we do start to see some times when this happens just by chance, but it's only 13 out of like 16,000 trial runs, right? So the p-value here is very low, right? So so this is something we've done before. What's new here? What's new is that we are going to use the normal distribution here. Okay, so remember what the p-value is. It's the proportion of the dots that are as extreme or more extreme than p hat. Okay, so if I think of this null distribution as the normal, so I'm going to click this box over here, and it's kind of subtle, but I think you can see it. It's got that little, it's got the blue normal curve that appears on top of the dots. And we see that, yeah, the stacked dots there actually are very, pretty close to the normal distribution. So here's what we're going to do in the next, in chapter 3 and afterwards. Instead of counting dots in the randomization applet and seeing what proportion of dots are greater than p hat, we're going to see what proportion of the normal distribution is beyond p hat. So it's a very similar idea. Okay, so what's our p-value here? The p-value is 0.0008. Let's just write that down. Okay, so from our dots, from our randomization applet, we got 0.0008, very similar to what we got earlier when we talked about that study. So that's the chapter 2 method. That's the randomization applet. It's great. We love it. We use that a lot in stats. But here in chapter 3, we want to use the normal distribution. Okay, so how does that work? Well, to use the normal distribution, you need a z-score. Okay, so let's remember the formula for the z-score. It's x minus mu divided by sigma. Okay, so x is the observed value, mu is the mean value, and then sigma is the standard deviation. And what is standard deviation? It's a measure of the spread, right? So the z-score in the context of the hypothesis test, what we're going to do is for the observed value x, we're going to use our point estimate, p hat. Okay, for the null for mu, we use the null value. Okay, so the null value 0.5 in the head turning study. Then for sigma, for the standard deviation, we use the standard deviation for p hat. Why does that say standard error instead of standard deviation? Well, it is a standard deviation. The standard error is a standard deviation, but it's the standard deviation of p hat. Okay, p hat is the point estimate that's that we're using to try to estimate p. So it's a single point on the number line that's estimating p. We call it the point estimate. So the distance p hat is from p is an error, and so the spread in p hat is called the standard error. Okay, so the standard error is a standard deviation, but it's a particular kind of standard deviation for a point estimate. Okay, so It's the same formula, it just looks a little bit different. Instead of x, we have p hat, the point estimate. Instead of mu, we have the null value. And instead of calling it the standard deviation, we call it the standard error. But it still is very much a z-score. So let's use the z-score to find the p-value for the head-turning case study. Okay, so we're going to use the formula above. Okay, so we have the point estimate minus the null value divided by the standard error. So the point estimate is that 65%. Okay, so we go 0.645. Then we put in the null value, which is 0.5. Then we divide by the standard deviation, also called the standard error in this case. Now, there's a formula for the standard error that we're going to learn later. For now, I'm just going to tell you the standard error value. Okay, so it's 0.045. What that means is that your typical p hat will be within about 5% of the null value there. Okay, so we calculate that z-score. Let's go ahead and do that. So we go 0.645 minus 0.5, then we divide that by 0.045, and we get a z-score of 3.22. So what does that mean? It means that this p hat of 65% is more than 3 standard deviations away from the null value. Okay, where are you in the normal distribution if you're more than 3 standard deviations away from the middle? You're very far out in the tail. Remember the 68, 95, 99.7 rule? By the time you get out 3 standard deviations, you're including the vast majority of the population. And so this p hat value that the guy got from his study is even beyond that. So it's very strong evidence against the null. Okay, and that's why we reject it, right? So we can take that z-score and use it to find a p-value. Okay, so he's 3.22 standard deviations. In the context of hypothesis testing, we call those standard errors from the null value of 0.5. So if we jump into GeoGebra here, we can find the p-value. Okay, so we go to GeoGebra. It's not asking us to do this in the lecture notes, but I just want to kind of complete the circle here a little bit. So we're going to go to the probability calculator. We're going to go to the standard normal. Okay, this is a one-tailed, right-tailed test. So we're going to see what is the probability of getting a z-score of more than 0.322, 3.22. There is that probability. You can see it way out here in the tail. It's a very tiny region. If they didn't have that little triangle there, you wouldn't even be able to see it probably. But it does exist. It's 0.0006. Okay, so 0.0006. So there's 2 different p-values, one from the randomization applet, one from the normal distribution. So they are different, but they're basically saying the same thing, right? They're saying that it's very unlikely you would get a p-hat of 65% if the null value is true. So we turn that around and we reject the null. See how that works? So we now have a second way of conducting a hypothesis test, and that's great. And probably it's more common to use this normal distribution than the randomization applet. Okay, so we do like the randomization applet. It does get used a lot, but the normal distribution gets used even more. Okay, so it's good. It's one more tool that we have. Okay, so let's do one more, and then I think we'll be in a nice spot here with the normal distribution for today. So, any questions about that example? So it's doing the same thing, but in a different way. We're basically calculating a p-value to make a decision about a hypothesis test. Okay, let's do another one. So in chapter 2, we talked about a study where a medical consultant claimed that her group of physicians did better than the national average. So I think we talked about this example. It is in the text. Uh, I believe it was for liver transplants. It was either liver or kidney transplants. And what it says is that the national average for complications when it comes to liver transplants is 10%. So, in other words, 90% of the time these liver transplants are successful, but 10% of the time there's a complication, unfortunately, right? So, on one hand, that's good. The vast majority are working. On the other hand, there's still some room for improvement. And so that's what this medical consultant was saying. She said the group of surgeons that she works with has a better complication rate than the 10%. Okay, um, so the null is that their group is the same. The alternative is that their group is different from the 10%, right? So how do you go about testing it out? Just because she says that her group is good doesn't mean that you should necessarily uh, adopt their techniques, right? We need to be, it needs to be proven that they're doing well, right? That they're doing better. So she got, um, I believe that, yeah, it was 62, right? And so she had, darn, now I've forgotten the numbers. Let me write the numbers down here real quick. So it was, forgot to write this number down. Let's see here. Okay, yeah. So basically they had 62 clients and there were only 3 complications. Okay, so they had done this procedure, this transplant 62 times and only 3 of them had resulted in complications, right? So if we look at our p hat for the sample, that's 3 out of 62 for a p hat of 0.048. So that's about a 5% complication rate. 5% is not 10%. It is indeed different from 10%. But is it so far away from 10% that we're convinced? Is this statistically significant? Okay, so if we go to our applet, we can answer that pretty quickly, right? So let's do this in the chapter 2 way first. So in the chapter 2 way, we would put in the null, and then we put in the sample size, 62, right? And then she got 3 complications, right? So that's our boundary, right? And then so we draw the samples. Let's turn off the normal and hide those. You guys remember doing this, right? So we did this in class, and the p-value here is 0.1540. It's just not quite convincing enough, right? It's a fairly high p-value, right? So that's using our applet, the randomization applet. That's what we did in chapter 2. How do we do this with the normal distribution? Okay, so with the normal distribution, we need the z-score, right? So let's calculate that. So it's the p hat, right, for the observed value. So we go 0.048. Then we put in the null value of 0.1, and then we divide by the standard deviation. Now, again, in the context of hypothesis testing, the standard deviation is typically referred to as the standard error. Okay, and so later I'm going to show you the formula for that, but I think it's better if I just tell you what the standard error is here, and then later we'll study the formula. Okay, so we put that in, we calculate that z-score, so 0.048 minus 0.1, and then we're going to divide by 0.027, giving us a z-score there of about negative 1.93. Okay, so, oh, I forgot. This is a two-tailed test, right? So what do we have to do? We actually have to double it, right? So we hit the two-sided. So the p-value actually goes up. It's even higher, right? The 0.2330. Okay, so from the randomization applet, our p-value is 0.233. Let's do this with the normal distribution. So we go back to GeoGebra and we say, okay, what's the probability that z is to the left of negative 1.93? Okay, so we go to GeoGebra this time, and we're going to say less than negative 1.93. Okay, but this is a two-tailed test, so I can go outside of, so less than negative 1.93 or greater than 1.93. So it's a two-tailed test, and we can calculate the p-value that way. Okay, so so how many standard errors from the null value are we in this case? 1.93 standard errors. Okay, all right. So any questions there about that? It's another use for standard deviation, and it's a way of using the normal distribution to do hypothesis testing. Right, and we're going to do this quite a bit. This is just kind of the first look at this. Are there any questions about that before we move on? Okay, so now we're going to do something totally new. We've never in this class yet talked about confidence intervals. Right, so confidence intervals are the second of our two major types of inference that we do in stats. Okay, so remember, inference is where we use a sample to try to make a statement about the whole population. Okay, so far, the hypothesis test has been it, right? I mean, that's the only kind of inference we've done. Well, the other major kind of inference is confidence intervals. Okay? And these get used quite a bit. Okay? Are any of you following the upcoming presidential election? Do you read polls about that? If you read polls, you're basically looking at the result of a confidence interval. Okay, they love using these confidence intervals because they provide an estimate, but then they also will provide what's called a margin of error that gives you an idea of how accurate and precise it is. Okay, so we're going to take a deeper look at confidence intervals because they're used throughout stats. They're highly respected and used in various quantitative fields. And so yeah, we're going to be doing this for the rest of the semester, these confidence intervals, and we're going to learn how to calculate them as well. So first of all, what is a confidence interval? It's a plausible range of values for the population parameter. Okay, so we have a parameter that we're trying to understand. And what the confidence interval does is it gives you an interval of values that are plausible for that population parameter. Okay, so there's a formula for it. Right? And so the most common confidence interval is the 95% confidence interval. The way it works is we take our point estimate, we put it in the middle, and then on both sides of p hat, okay, so it's plus and minus on both sides, we attach a margin of error. Okay, so that margin of error has a formula. It's about 2 standard deviations. 1.96 more precisely, but 1.96 is pretty close to 2. Okay, so haven't we talked about going up 2 standard deviations before? Yeah, the 68, 95, 99.7 rule, right? It says if you go out 2 standard deviations, you capture the middle 95% of the population. And that's basically the same idea here. It says if you go 2 standard deviations away from p hat, you're going to capture the middle of the distribution about 95% of the time. Okay, so these are fairly complicated objects. They're not probably as difficult as the hypothesis test, but still they have lots of pieces to them. So let's kind of take it slowly here as we go through these examples. I'll come back to that example here after we look at sort of the language of confidence intervals for a little bit. Okay, so let's look at several of these examples. So we have the results of a Marist poll. So Marist, again, it's another one of these well-respected professional polling companies. there's a number of them that are, many of them are quite good and well respected, using good scientific techniques, nonpartisan. They interviewed more than 1,000 American adults and asked them about um, uh, road testing, driving testing, right? So you know how this is, right? Among elderly drivers, as you get older, it's kind of sad, but it's true that your reflexes do start to decline at some point. Maybe your eyesight probably will decline, and it just happens, right? So the idea is that at some age, maybe we should have a cutoff where we require elderly drivers to come in and get retested, right? We don't necessarily want to take their driver license away from them if they're healthy and they can drive. We don't want to punish them, but if it's unsafe for them to drive, we should probably, uh, you know, take the license away. Yeah. So the idea is, okay, well, 65, that's sort of a typical age for, thinking about like senior citizens. um, Maybe we should at the 65th birthday have them come in and get a road test, right? Driving test. Um, so it sounds like a good policy, but maybe it's not a popular policy. Maybe everybody hates that policy, right? Or maybe everybody loves it. So what they did is before they put the policy in place, they want to understand how people think about it. So they have a sample, pretty big sample, and they just ask people, hey, how do you feel about requiring people when they hit 65 to come in and get a road test? Okay, so of those 1,018, 672 said yes, we think this is a good idea. Okay, so what kind of data is this? Well, either you're in favor of it or you're not, right? So this is categorical data, right? So we know that we're looking at P, the population proportion, right? So this is the proportion of all adults, all American adults, in favor of the road test. Okay, so good. All right. So that we're going to do the inference using p hat, right? That's our sample. We need a sample before we can make a decision. So the sample size is 1,018. The number of successes is 672. Okay, so if we do that, calculation here is a 672 divided by 1,018. We get about 66% of people saying that they are in favor of that policy. My guess is that older folks are less favorable to this test, right? They don't want to be inconvenienced with the test. Younger people are probably, more in favor of it, right? But overall, it does look like there's pretty broad support for this. It's definitely a majority think this is a good policy. So probably it's something that they want to consider putting into place, right? Okay. So if you read this poll, they talk about the 66%, but then at the end, they say we have a 95% confidence level for our confidence interval of 0.631, comma 0.689. So what is that interval? Well, the confidence interval is a list of plausible values for P. Okay, so here's the idea. P, which is the proportion of all adults who favor the test, has to be between 0 and 1. The least it could be is 0, right? I mean, you could have the case where nobody wants this test to take place. The other extreme could be 1. You could have a case where everybody wants it to be, wants this test to be, in place. But of course, it's not going to be those extremes typically, right? It's going to be somewhere in between, and maybe it's right here, right? So there is P, but nobody knows exactly what P is because there's hundreds of millions of adults, and nobody has the money or the time to call and track down and talk to all of these people, right, and ask them their opinion. Okay, so we get a sample. Okay, and then that sample is p hat P hat will typically not be exactly equal to P because of sampling error. So that value there is the 0.66. Okay, so you see 0.66, it's between 0 and 1. Then, because there's sampling error, we don't, we're pretty sure that P hat does not hit P exactly. So what we're going to do is we're going to build a margin of error on the left of P hat, right? So we go out a certain distance there, and then on the right, and then on the left, we go the same distance, and we put another margin of error on the left. Do you see how that creates a confidence interval that's symmetric about P hat? P hat is the midpoint of the interval. And the way I've drawn it here, we see that P is captured by that interval. Okay, so we have a list of plausible values. So you can think of the confidence interval as a net. It's like a one-dimensional net that we're throwing at the number line between 0 and 1 with the hopes of capturing P. Okay, so what's the right end point of that net? That's the 0.689. What's the left end point? That's the 0.631. Does this graph make sense to you guys? This drawing here. So it's a list of plausible values that capture that could possibly equal P. So how do we interpret this? What exactly is that confidence interval saying? Well, just like there's an interpretation for the hypothesis test results, there's an interpretation for the confidence interval results. And it too is also formulaic and sort of a boilerplate interpretation, which is good. Sometimes it's nice to have, just kind of a formula that you can rely on. And so it goes like this. It says, we are, or there is, we state the level of confidence. Okay, so we're 95% confident that the true proportion of, and this is where if you want to lose all of your points, you talk about the sample. Okay, so if you say that the true proportion of the 1,018 who are in favor of the test, if you say that, then you lose all of your points. Okay, what we're doing here is we're doing inference, and we're talking about the whole population. Okay, so we're talking about the true proportion of all, and you can emphasize it there if you want, all American adults who are in favor of drivers being retested upon reaching 65 years old. Okay, so it's pretty formulaic. So what's the formula? The first part is we tell people what the confidence level is. Okay, so maybe I should say that a little bit differently. I shouldn't say confidence, I should say confident. Okay, so we're 95% confident. Okay, so that's the first part. You tell people how confident you are in the confidence interval. Okay, so some confidence intervals we have greater confidence of capturing the parameter. Others have less confidence. Okay, and we'll talk about how we know what that level is and how we select the correct level. But for now, it's 95% confidence. So 95% confidence that the whoops, I am not having a great day. We're 95% confidence that, my apologies, oh my goodness, I forgot to write the interval in here. Okay, so that the interval from, we have to tell them what the interval is. Oh my goodness, sorry about that. 63.1% to 68.9%. Okay, captures, there we go, the true proportion of all American adults who are in favor of drivers being retested upon reaching 65 years old. Okay, yeah, thank you, Polly. So what are the pieces here? We have to tell people what the confidence level is, then we tell them what the interval is, and then we tell them what it is we're trying to do with this interval, right? We have an interval of numbers, What are we trying to do with it? We're trying to capture the true proportion of all American adults who are in favor of drivers being retested upon reaching 65 years old. Okay, so it's just follow the formula. Okay, you start with the level of confidence, then you tell them what the interval is, and then you tell them what it's trying to capture. Okay, and it's got to be some proportion in there. I'm sorry, some parameter in there. Here I've used percentages. If you want to leave it as a proportion, I'm 100% fine with that. I do think that when you're communicating results to readers, that percentages are a little bit easier to understand, but I'm fine with proportions there. I tend to write percentages myself, but okay. What do you guys think? Okay, so I encourage you, if you follow politics at all, especially if you read polls, go look at the fine print of the poll, the next poll you see for the election, and they probably will have a confidence interval for you. Okay, so they'll tell you the confidence level, and very often it's 95%, and then they'll tell you what the margin of error is. Okay, so these confidence intervals are used everywhere. Political scientists love them, but they're used in medical research, they're used in economics, they're everywhere. Okay, so very, very important inference technique here. So that's how we interpret the results. I haven't shown you the formula here yet, but I think that gives you the general idea. Okay. Let's see here. Got a question. Sorry, I know you went over it, but how do you know where to put P on the graph? You don't really know because it's unknown, right? So I just kind of put it on there. It'll typically be pretty close to P hat. If you talk to 1,000 people, you're going to get a pretty good idea of what P is if it's a random sample. So what I'll typically do is I know what P hat is, right? It's 0.66. So I just put P pretty close to 0.66 because I knew P hat is probably not going to bounce too far away from P. Does that answer your question, Killian? Um, so so I think the idea of an interval makes sense. The parameter makes sense to you guys. This idea, though, of the level of confidence might strike you as a little bit weird. Why don't we want to have 100% confidence? Well, if you're using a sample, you never have 100% confidence, right? It's kind of like with the type 1 and type 2 errors with hypothesis testing. If you're using a sample to make a decision, or if you're using a sample to make a confidence interval, there's always a chance it'll miss P. So we never can have 100% confidence. Okay, so 95% confident is a good and common level. 99%, 90%. These are kind of typical values. What does 95% remind you of? If you're 95% confident, then you're 5% unconfident, or I don't know how you say that exactly, but there's a 5% lack of confidence, right? Does alpha equal 0.05 kind of ring a bell? It's sort of a very similar idea, right? Alpha equals 0.05 is the probability of a type 1 error of your hypothesis test being wrong. And the 5% lack of confidence is, it's kind of giving you an idea of how likely it is your confidence interval misses, right? So it's very similar to alpha. So 95% is a common confidence level, 99%, 90%, okay, corresponding to alpha equals 0.01, 0.05, and 0.1, okay? So there's a really nice applet that we have that gives us an idea of just kind of a visual idea of how this would work. So let's say we're studying IQ, okay? And then so let's say the average for this particular IQ test is 100. So the middle of the distribution is 100. And let's say we're building confidence intervals to try to capture that average or middle value. Okay, so if we're building 95% confidence intervals, what does that mean? Well, if we're 95% confident, then if we built lots and lots of the intervals, we would expect the intervals to capture the parameter about 95% of the time. So if it captures it 95% of the time, then it's going to miss sometimes. and we're okay with that. We don't want it to miss a lot, but every now and then it's reasonable because we're working with samples. So what this graphic is it's 100 confidence intervals, okay, and the parameter is 100. So the goal is for the interval to capture that red line. In other words, if the black line, which is the confidence interval, straddles that red line, then it's captured the actual parameter, and it's been a successful confidence interval. Just by looking casually, you can see that the vast majority of these do capture the red line, right? Some of them get it right in the middle. Others, like this one, it still captures it. It almost misses, but it still captures. But there are a few where it totally misses. Okay, do you see where those are? Just kind of have to look down through there. It looks like it misses there. Looks like it misses on this one, misses on this one, maybe this one, and this one. Okay, those look like misses to me. And how many is that? About 6. Okay, so the confidence interval, the 95% confidence interval, is saying that we're expecting it to work about 95% of the time. We're expecting it, in other words, to miss about 5 out of 100 times, and that's pretty much what happened, right? I mean, it missed 6 times, but this it's random, right? So we're expecting a little randomness there. So it basically worked as advertised, right? And so let's do this a little bit more dynamically by using our applet. And I think that'll give you a nice idea of how this works. So it's the same applet that we've worked with before. I'll put it in the chat if you want. You don't need to use this because it's not really going to be relevant to your exam or anything. You don't have to do this on the exam, but it is kind of fun to play around with this. So we go to that. I put it in the chat if you want to do it along with me here. So if you look at this exploring randomness, it says simulating confidence intervals. So let's kind of simulate that IQ example again. So let's say the mean is 100, okay, and we want to do maybe samples of size 50. Okay, so every time I hit the button here, and this is a 95% confidence level, it's going to take a sample of 50 from a population whose mean is 100, and using the formula that we haven't discussed yet, it's going to calculate a confidence interval. Okay, so I hit sample, and what do we get? We get the center line, which is the parameter that we're trying to capture. It's kind of tiny. Let me see if I can make that a little bit bigger here. But I think you can tell that, yeah, it does capture the parameter. It almost missed, but it did get it, right? So it's green. If I do that again, we get another one. You can see they're kind of bouncing around a little bit because they're based on a point estimate from a sample. So most of the time it works. Okay, so if it's a 95% confidence interval, we'd expect it to work about 95% of the time. So let's make this a little bit faster here. Let's do 100 samples. From each sample, we'll calculate a confidence interval, and then we'll see if the confidence interval captures the parameter. Okay, so the parameter again is 100, and we have 100 confidence intervals. When it works, the confidence interval is green. When it misses, the confidence interval is in red. Okay, you guys see that? Okay, so how many times did it miss? 1, 2, 3, 4, 5. So it worked exactly as advertised, right? 95% confidence. So they are going to miss sometimes. Okay, and that's a whole nother important thing to consider. We'll talk about that later. Okay, so if there's 95% confidence, could there be more confidence or less confidence? Yes. Let's do 99% confidence. Okay, so all eyes on the app here. I'm going to hit the sample button. It's going to calculate 100 random samples from a population with mean 100. And for each of those samples, it's going to build a 99% confidence interval. Okay, so earlier I said a confidence interval is kind of like a net, a one-dimensional net we're throwing at the number line with the hopes of capturing the parameter. Okay, so if I want to increase the likelihood of capturing my parameter, what do you do to the net? Okay, so if you're throwing a net trying to capture something, aren't you going to be more confident if the net is larger typically? Yeah. Okay, so watch what happens to these green lines. They should get a little bit longer. Okay, so everybody watch as the green lines get a little bit longer. Do you guys see that? Okay, so a 99% confidence interval is going to be wider than a 95% confidence interval. Just like a larger net gives you more confidence than a narrower net. Right? How many times does the 99% confidence interval miss? It looks like it misses twice. Okay, so yeah, twice. It's pretty close to one. So it pretty much works as advertised. Let's go in the opposite direction. Let's go to 90% confidence. Okay, so if we're less confident, then the interval should be narrower, right? So I'm going to hit the button, and I want you to watch those green lines shrink down a little bit. Did you see that? Okay, so the green lines shrink down, and we start getting more misses here, right? So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 misses. Okay, so we're expecting about 10 misses. We get 12 misses. That's, there's randomness here, so it's not going to be exactly 10, but pretty close to 10 misses, right? Okay, so you guys kind of getting the picture here. That we're going to look at the formula. Don't worry. There's more to it. It's just kind of one piece at a time here. Okay, so that's what this diagram is about. It's helping us think about how the confidence interval does miss sometimes. We don't like it, but we're kind of stuck with it because we're using samples. Okay, let's do another one. All right, so this sample came, let's see here. Let me do this one, and then I'll have you guys do that one. Yeah. Let's say you're a data analyst at in the at a big university. Okay, so big universities they'll definitely have like a data science team. Slick has a data science group, so we've got data analysts, data scientists who look at all sorts of statistics about things at the college. So let's say that we're trying to figure out the proportion of students at a university who smoke. Okay. How would you figure that out? I'm pretty sure that there's no data set that the college has that tells, how many students smoke, right? I mean, it's just not something you ask typically, right? I mean, when people apply for college, you don't say, well, do you smoke, right? No, they don't know, right? So, but it's still relevant to the kind of, the health, right, of the student body. So if you're interested in that sort of thing, the only choice you would have is to take a sample, right? So let's say we have a random sample of 200 students, and of the 200 students, 40 were smoking, said that they smoked. All right, so how would we build the confidence interval here? Okay, so what is the parameter? What's the parameter we're trying to capture? P is the proportion of all students who smoke. Okay. Either you smoke or you don't, right? So it's categorical. So it's P that we're looking at. Okay. So it can't be less than 0. It can't be more than 1, right? The least it can be is 0. It could be the case that nobody there smokes. At the other extreme, it could be that everybody smokes, so it's 1. But that's just not going to happen in the real world. In the real world, it's going to be smaller, right? So maybe it's right here. Who knows, right? So how do we investigate that? We take a sample, right? So we take our sample and we calculate p hat. So p hat is the point estimate. It's the number of successes divided by the sample size. So a success here is being a smoker, right? So, not necessarily a good thing. It's just the word we use for the category of interest. Okay, so 40 divided by 200, that's 20%, right? Okay, so our p hat is 20%. And then we know that p hat almost certainly misses p. We don't know if it's above or below, but just because of sampling error, we're expecting it to be a little bit off. So what we do to make up for that is we build a margin of error on the right, and then we build the same margin of error on the left. Okay, so that creates a symmetric confidence interval around p hat. Okay, so we're told what that interval is. Don't worry, before too long, you'll be calculating it yourself using the formula and using software. Let me make some space here. It's kind of small. Does that make sense? So we got this plausible list range of values ranging from about 15% all the way up to about 25%. So it's plausible that it could be as few as like 15% of students who are smoking, or it could be as many as 25% smoking. Okay. So the point estimate is 0.2. That goes right in the middle of the interval. What is the margin of error? Well, the margin of error is the distance from the center, the point estimate, to the endpoint, right? So we have 0.2 in the middle, and then at the endpoint there we have 0.247. So if I subtract the midpoint from that right endpoint, I get my margin of error of about 5%. Okay, so the margin of error there is 0.047. That's a very common kind of amount for a margin of error, about a 5% bouncing around for p hat. Okay. So what is our interpretation? Well, we have the same three-part interpretation. Okay, we start by telling people what the confidence level is. So we are, or there is, 95%, okay, confident. 95%, we're 90% confident that the true proportion of, okay, so if you want to lose all your points, then you talk about the 200 students, right? Okay, we're not talking about a sample here. We're talking about the whole population, right? So that the true proportion of all students at the university, let's see here, yeah, at the university who smoke is captured by the interval from 15.3% to 24.7%. Okay, do you see those same three elements there? So we start by saying what the confidence level is. Then we talk about, I did this in a slightly different order than the last one, but it's perfectly fine. We talk about what the confidence interval is, right? And then we talk about what the parameter is that we're trying to capture. Okay, so those are the three things you need. Okay, so you need to state the confidence level, then you need to tell them what the interval is, and then you also need to tell them what parameters you're trying to capture. Okay, and again, make sure that you're talking about all, all people or whatever it is in your population at this point. We don't want to talk about all the people in the sample. We don't need a confidence interval for a sample. We know what the sample proportion is, right? We don't need to estimate that. It's 0.2. What we're trying to estimate is P, the population parameter. So I want you guys to try one of these. Okay, I still haven't shown you how to find the margin of error really, or calculate the confidence interval, but we'll get to that. You just have to kind of think about what this means first before we start pulling out the formulas. So you guys try this one above. We have another poll. This one coming from the Gallup organization. So Gallup, it's a very large polling company. Perhaps it's the largest. Very prolific. They do all sorts of polls about all sorts of different things. In this case, they were looking at the confidence that people have in the news, and especially the television news, right? So they asked people, do you trust television news a great deal or quite a lot? Okay, so basically, either you do or do not have a lot of trust in television news, right? So it's categorical. Okay, so P is the proportion of um, people, American people who trust a great deal or quite a lot TV news. Okay, but we don't know what that number is. We don't know what that proportion is, um, because you can't talk to everybody in the country, right? So what we do is we do a sample, and well, they did a sample, and they said that the sample proportion is 19%. They tell us what the margin of error is. I want you to tell me what the confidence interval is, and then I want you to write an appropriate interpretation. Okay, so it's a little bit different than the other ones that I've done, but it's same idea. You're going to have p hat in the middle. You're going to add the margin of error on the right. You're going to add the margin of error on the left. So basically, guys, it's going to be 19 plus or minus 4. Okay, so use that to calculate the two endpoints of the confidence interval. Then I want you to do that three-part interpretation for the confidence interval. I'm going to go quiet for a couple minutes. If you want to join one of the break rooms, one of the breakout rooms, I will open one up for you guys. It's totally up to you if you want to join that. And then, so I'll give you about, let's do maybe 4 minutes on this. We'll come back at 12:32 and talk about this together, okay? So I'll go quiet and let you guys work on this for a little bit. Okay, anybody get it? What are the two endpoints here for this confidence interval from Gallup? If we go 19 plus 4, that should give us the right endpoint. If we go 19 minus 4, that should be the left endpoint. So the interval is ranging from 15% to 23%. We wrote that as a proportion. That would be 0.15, 0.23. So you can use percentages or proportions here. They're both fine. My rule of thumb is if I'm going to be doing calculations, then I prefer proportions. But then for reporting results, I tend to use percentages. Okay, so can anybody tell us what their interpretation is for this? I've done a few of these now, and so I would love it if somebody else were to speak up here and tell us how to interpret the interval. All right, let's see here. So here's what Armand has in the chat. I'm just going to copy and paste it right here, and then we can look at it and see what we think. We're 95% confident that the true proportion of all Americans who trust TV news is captured in the interval from 15% to 23%. Perfect. Couldn't have said it any better. This is exactly right. Okay, so who cares about this sort of thing? Well, I mean, people who are interested in the media, interested in public opinion. So if you're into like political stuff, or just kind of studying the media, this is useful and interesting to you. So so what is it saying? Well, trust in the news TV is not very high. It could be as low as 15% of people have a lot of trust in it, or it could be as high as 23%. So even at the high end, it's still not very high, right? So there we go. All right. So we're on the right track. I mean, there's still some stuff to do here, but we have the beginnings of an understanding of how these confidence intervals work. Let me just have you guys do one more, just a quick multiple choice. Here we're looking at fireworks. So they're trying to figure out what percentage of people are going to do fireworks. So, people who work in that industry would like to have an idea of, how many fireworks that they should be stocking up on so they can sell them, right? So how many people are going to do fireworks? So this isn't across the whole country. They're looking at people in Kansas. So they asked 600 Kansas residents whether they plan to set off fireworks on the 4th of July. And this polling company came up with a confidence interval to 99% confidence that, and so the interval is 0.501 up to 0.612. So which of the following is the correct interpretation of the confidence interval? So just read through those real quick and then put your answer over in the chat. And then we'll talk about which ones are correct, which one is correct, which ones are incorrect, and we'll talk about why they're incorrect. Okay. So I've got a C, I've got a couple of D's in there, and I think D is the best. So let's go through this. So 99% of Kansas residents will set off between, no, that's just wrong in so many different ways. We're really careful to not talk about probabilities. We prefer the language of confidence. So we don't want to say there's a 99% probability. So let's see. C is sounding pretty good. We're 99% confident that the interval between captures the proportion, but the problem here is that it talks about people in the sample. Okay, so we have no need to build a confidence interval for the sample proportion. We know what the sample proportion is, right? So that's the problem there. This one doesn't even talk about a confidence level, so yeah, it's got to be D there for that. Great. So we're getting there. Now what? Now we need to lay the foundation for understanding the formula. So we do provide the formula up here somewhat. We talk about the 95% confidence interval. So what we do is we take our point estimate, p hat, and then we add and subtract. So you see that plus and minus. So it's a shorthand notation for saying plus and minus about 2 standard deviations. Okay, and intuitively that should kind of make sense because we know that with the 68, 95, 99.7 rule from last time, if you go 2 standard deviations out, you're going to capture about 95% of the distribution. So that works in reverse. If we start at p hat and we go 2 standard deviations away from p hat, we should capture the population proportion about 95% of the time. Okay, now we don't want to be stuck at 95% confidence. We'd like to be able to bump that up to 99%. We'd like to be able to go down to 90% or even below that. So how do we do that? Well, what we're going to do, instead of use 1.96, we're going to use a dial. Okay, so it's still the p hat. It's still the standard error here, and it's still adding and subtracting. But to get the margin of error, we want to have some flexibility. So if we want to have a 99% confidence interval, we're going to dial up that number a little bit. Okay, so instead of 1.96 standard errors, we might go out 2.5 standard errors, right? Or if we want less confidence, we can dial that number down. So the dial is called Z star. And the other name for it is it's the critical z-score. Okay, now some of these levels are quite common. So we've actually got a table of these values for the critical z-score. Okay, so if you want to be 95% confident, you go out 2 standard deviations. If you want to be 99% confident, you have to dial it up to about 2.58 standard deviations. If you want to be 90% confident, you dial it down to 1.65 standard deviations, okay, etc. Okay, so we like that little dial there, the critical z-score, because we can customize the confidence interval any way we like. We can make it larger, we can make it smaller, and we like that. Okay. So let's practice with that little dial. Let's say, and it's a little bit eccentric, but let's say instead of a 95% confidence interval, we want a 96% confidence interval. How would we find our Z star? So we cross our fingers and we hope for a 96% confidence on the table, but we don't see it. We have 95, but then it jumps up to 90, 98, right? So we don't have a 96. So we have to use GeoGebra. It's actually very easy. So let me show you how this works. If you want to have a 96% confidence interval, then what you do is you go out a certain distance from p hat. Okay, so you need to go out a certain distance from p hat such that you capture the middle of the distribution 96% of the time. That's equivalent to going out a distance from the center of the distribution such that you capture the middle 96% of it. So it's the z-score. So we're going to be in the standard normal, and we're going to go out far enough so that we capture the middle 96% of the distribution. So how far out is that? Well, does this kind of sound like what we were doing last time? Yeah, it's exactly what we were doing last time. So if I have to go out, if I want to capture the middle 96%, how much does that leave for the two tails? 4%, right? So that 4% is split into 2 pieces, one on the left and one on the right. Okay, so we split that 4% into 2 pieces. So we have a 2% down here, and we have a 2% over here. So the idea is, if you want to be 96% confident, you have to go out far enough in the distribution such that 2% of the distribution lies beyond that point. Didn't we learn how to do this last time? How far out in the standard normal do you have to go such that only 2% is further than that value? That's exactly what we're doing last time. So let's open up GeoGebra. Let's clear everything out. Start from scratch here. We're going to go to the three dots. We're going to go to the probability calculator. We're going to go 0 for the standard normal mean of 0, 1 for the standard deviation of 1, and then we're going to say greater than, and we want the value greater than to be 0.02. So the area, the probability, the proportion is on the outside. The observed value, in this case a z-score, pops up on the inside. So that's 2.054. Okay, so that would be the critical z-score required for building a 96% confidence interval. So think of that critical z-score as like a dial, right? If you want to be more confident, you make it a little bit larger. If you want to be less confident, you make it a little bit narrower. Okay, you make it the z-score a little bit smaller. Okay, on exams, we'll always choose levels that you can find here on the table. Okay, all right. What now? Well, now we want to set the foundation for understanding the formula for the standard error. Okay, so we understand. Well, let's see the formula. Let's look at the formula. Okay, we understand the margin of error. We understand z star now. What we haven't really discussed is this part here with the standard error. Okay, so what is the standard error? It's a standard deviation for p hat. So there's a formula for it. I told you there's a formula. It's right here. It's on the formula card. We want to understand this formula a little bit more. Where does it come from? How do we calculate it? How do we use it? Why is it true? That sort of thing. Okay. So let's read through some of the vocabulary here, and we can get started. I don't think we'll finish it, but we have a little in-class activity that we can begin here today. Are there any questions out there? Not getting a ton of questions today, so just want to make sure you guys are feeling all right about everything. Okay, so we've talked about some of this before, right? We've used language like trial, success, and failure, right? So a trial is a single event that leads to an outcome. We've always been looking at categorical data so far, right? So we've had successes and failures. So like a right turn was a success, the baby choosing the helper was a success, stuff like that, right? Okay. And then it's not necessarily the success is a good thing, it's just the name of the category that we're interested in. So we add up the number of successes and then we divide by the sample size. That gives us our sample proportion. Nothing new there. We've seen that formula before. Okay. So earlier I made the claim, let's see, do I still have that graphic up? No, I've lost it. Never mind. I made the claim that p hat can be normally distributed. Okay, so think of our applet where we have the dots and we're looking at the dots and they created that nice bell-shaped normal distribution, right? So that does, and it can happen that p hat is normally distributed. It doesn't always happen though. Okay, certain conditions have to be met. So there's 3 conditions. The data have to come from a random sample or a randomized experiment. Okay, they have to be independent of each other. So the people in the sample don't really know each other. They're not influencing each other. And finally, we have to have a large enough sample such that we get at least, we get enough in both categories. Okay, so if you're trying to estimate the proportion of right turns, well, you need some in both categories, right? You need some right turns and some left turns. If you get a sample and everybody's turning their head to the right, 100% of the time, it's kind of hard to estimate the number of left turns, right? So we need to have enough in both categories. And the rule of thumb is we have 10 in the success category, we have 10 in the failure category. If those three conditions are met, then p hat is approximately normal, and we know what the standard error is. Okay, the standard error will be p 1 minus p divided by n. Okay, so you can prove this if you know a lot of calculus and more advanced math. We're not going to prove it here. Calculus is not a prerequisite for this class, but we are going to verify that this is true. We're going to run some simulations and we'll see that this formula is true. Okay, so this is the formula for the standard error of p hat. Okay, and what is that? That's the standard deviation of p hat. Okay, so this formula is on your formula card. You don't need to memorize it. You probably will end up memorizing it just by repetition. But if you don't worry, it's right there. So we're getting fairly deep into this formula card now, right? So if you haven't done this yet, I would print this off and just keep it with you when you're doing homework. And probably you want to take it with you to the exams too, at least part of it. So you might have forgotten where this comes from, so let me remind you guys. On our course homepage, so if you just come back over here to Canvas, if you scroll down to where it says formula cards, if you click on that, it'll take you here to version 1. So you just download that, and that's what I have here. This is the version 1 formula card. Okay, so what I want to do is show you that this formula is correct. This formula gives us an idea of how much p hat is bouncing around. Okay, so unfortunately, this activity that I want to do takes more than a minute, which is how much time we have today. So let me just show you what this is. And we're going to start with this on Thursday. We're going to use M&Ms to help us investigate the sample proportion and its behavior. We're going to show that p hat is normally distributed if certain conditions are met. Okay, so that's what we're going to do on Thursday. It's a nice class activity, and I think it works very well. So we'll do that on Thursday. We're pretty much out of time for today. Are there any questions as we break? Did anybody have a problem accessing their exam? Let's see here. Yes, so Sarah has a question about the homework in 3.2a question 9. Yeah, let's go through that. Let's go through that one together. So we're done with class. If you want to watch this example, you can definitely watch. If you don't, then feel free to sign off and I'll see you on Thursday. Okay, so let's see here. Let's go over to, thank you, Armand. Let's go over to 3.2 question 9. So let's see here. Okay, is this the right question, Sarai? This percentile? Okay. So yeah, your numbers might look a little bit different, but it should be the same idea. So we have light bulbs, and light bulbs eventually burn out. And then so some light bulbs last longer than others. And when if you've bought light bulbs before, you know that they kind of give you an idea of how long they're supposed to last, right? So if you want a light bulb that's going to last longer, you basically spend a little more money and they last longer. Or if you want to spend less money, you can buy a cheaper bulb and it just doesn't last as long, right? So that that lifespan, right? It's measured in hours. Typically, they might have other ways of measuring it, but that's a good way of measuring it. So they're saying here that the 81st percentile of light bulb lifespans is 1,500 hours. What does that mean? Any ideas out here? So the 81st percentile is the value in the distribution such that 81% is less than that value. Okay. So in other words, 81% of light bulbs have a lifespan less than or equal to 1,500 hours. So you're expecting your typical light bulb to go out before 1,500 hours. But there are some, about 19%, that last longer than 1,500 hours. Does that make sense? So it's an interpretation of the percentile. We're not really using a formula here. Okay, and then so is that another question there? Let's see, a distribution. So which question is that? Which one is that? Is that from a different section? Let me see here. Do you know what section that was from? I can pull that one up and then we can all look at it together. Three 3.2C. Okay, yeah, let's pull that up and have a look. No worries. Which number was that in that in that section? Number 9? Okay, let's see here. Okay, so we've got a distribution of values is normal with a mean of 150.1, a standard deviation of 61.3, find P90. So this notation here is the 90th percentile. So it's the value that separates the bottom 90% from the top 10%. Okay, so what is that? Let's see here. I'm gonna do some writing over here. So we have a distribution of values. It doesn't really tell us what it is we're measuring here. Maybe it's weights for, children or something. But it doesn't really matter what it is. It tells us everything we need. So it's saying the mean is 150.1. So that's mu. The standard deviation is 61.3. And we want to find the 90th percentile. So that is the value in the distribution such that 90% of the distribution is below it. So we know it's got to be more than 150.1. So how do we find the exact 90th percentile? Well, we use technology or the table, but just use the technology. It's much easier. So I put in the mean value, 150.1. I put in the standard deviation, 61.3, and then I say the area to the left, I want that to be 90%. Okay, so again, percentages, proportions, areas, probabilities, those are the values on the outside. The number on the inside is the value from the distribution. So 228.659, that should be the 90th percentile. So if you have that value for whatever it is that you're measuring in that case, then you are at the 90th percentile. Okay, so let's come back over here. Yeah, 228.7 if we round to the nearest one decimal place. Okay, how's that? Does that answer your question? Okay, great. Anything else out there that I can help you guys with? All right, well, have a good one and see you next time.